Hello, this lecture will cover pages 264 through 271 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 9E, the power factor. Starting on page 264, we're going to mention in detail the power factor. We talked about it before, but we're going to get into it in a little bit more detail in these next 10 to 15 minutes. Power factor measures the efficiency of electrical output. It is the process of analyzing the use of electrical power within a facility's electrical system. The power factor is the ratio of real power used to do the work to the apparent power supplied to the system or circuit. Power factors receive values between 0 and 1. When no real power is present, the power factor is 0. When all power is real, none is reactive, the power factor is 1. I'm going to paraphrase that a little bit. Whenever you have a purely resistive load, the power factor is going to be 1. Whenever you have a purely reactive load, the power factor is going to be 0. You'll see that in a minute. If a utility company's power factor is less than 1, it must supply more current to the system or user to optimize output. A large power factor is desired, while a low power factor is a result of inefficient electrical power measurements. So we said before that if you have a lot of inductive machines in your basement, a lot of lathes and presses running, you have a very large inductive load, that your power factor is going to be somewhat less than 1, and you're going to be using more power from the utility company than they're able to measure, because you're going to be using reactive power, and that's something that they can't evaluate without looking at something called a power factor. So let's look at it. We know that the average power is equal to Vmax times Imax divided by 2 times the cosine of the phase angle between the voltage and the current in watts. We talked about that. We also called that the true power. We could also look at it in terms of RMS. And we said that the true power or average power is equal to V RMS times I RMS times the cosine of this angle between the voltage and the current. Well, it turns out that this cosine of the value of the angle between the voltage and the current is equal to the power factor. Therefore, here, it's that simple. The power factor is equal to the cosine of the quantity phi v minus phi I, which we know is the impedance angle all the time. So here's the equation for the power factor. It's a number between 0 and 1 inclusive. It has no units, and it's the cosine of the impedance angle. You have to remember that. Let's take a look at the next page. Power factor angles. Since the cosine of an angle and the cosine of negative angle are the same value, the cosine of plus 45 and the cosine of minus 45 are equal. The cosine of plus 30 and the cosine of minus 30 have the same value. Since the cosine of angles in the first quadrant are equal to the cosine of angles in the fourth quadrant, what you have to do is you have to use terms like lagging and leading. And it always refers to the current with respect to the voltage. So, anytime there's an angle in the first quadrant, if you say there's a power factor of 0.8, you have to say the word lagging. The word lagging means that the current is lagging the voltage, and it is in an inductive circuit. So remember, we always said that any impedance angle that was in that first quadrant always indicated an inductive load. And down here in the fourth quadrant, the current is always leading the voltage because it's a capacitive circuit. Remember, any impedance angles we had in the fourth quadrant, impedance angles we're talking about now, in an impedance diagram, we always referred to them as as inductive circuits. When we took the cosine of impedance in this angle, it was always capacitive. It was always a capacitive circuit. So because the cosine of 30 degrees is the exact same thing as a cosine of a minus 30 degrees, when you're talking about power factor, you have to use the words lagging and leading. Anytime you say lagging power factor, it means it's an inductive circuit. Anytime you say leading power factor, it always is a capacitive circuit. And the words lagging and leading always refer to what the current is with respect to the voltage. That's the summary of this. So, well, I guess the summary's down here. Therefore, a lagging power factor means we have an inductive load, and a leading power factor means we have a capacitive load. So as a quick example, here we have a RL circuit. The impedance is equal to 3 plus J5 ohms. I'm giving you this. So in polar form, it's a 5.8 at an angle 59 degrees, and I want to know what the power factor is of this load. If this is a load representing a motor out here, if that's a load, and I asked you what's the power factor of that load, you have to know you have to know the resistance and the inductive reactance, or you have to know the impedance of that, or you have to know the voltage across it and the current through it, so you can calculate the impedance, so you can get that angle. Because the answer is the power factor of that load is the cosine of the angle 59 degrees. And it isn't good enough to just say 0.515. That won't give you, that's not the correct answer. You have to say 0.515 lagging. Because if that was a capacitor with a minus J5, you would get a minus 59 degrees and your power factor would still be 0.515. So you'd have to say leading. But in this case, there's your answer. Let's take a look down here at this example. We have a 200 ohm resistance. This right here is what's representative of our load, whatever it is. Now it's going to have a net effect here. It's going to be capacitive. You can see that the capacitive reactance of 800 ohms eliminates the 100 ohm inductive reactance. So you end up with a minus 700 here. But anyhow, this is what the load is modeled as. So the impedance here of the load is equal to 200 minus J700. So you need the impedance angle. So in polar form, it's 728 at an angle minus 74.1. I want to know what the power factor is of that load. The power factor of that load is equal to the cosine of a minus 74.1 degrees. So it's 0.274 leading. So just like up here, that has to be the answer. And you had to say the word lagging, otherwise it's wrong. Down here, the answer for the power factor of that load is 0.274, and you have to say leading. I give you, I think here, let's see, I give you 5 examples. We'll do a couple of them here. These examples are pretty straightforward. An industrial load consumes 100 kilowatts at a 0.8 power factor lagging. If an ammeter in the transmission line indicates that the current is 200 amps RMS, find the RMS load voltage. In all these examples and on the exam, you have to draw a diagram. If you don't, I'm not going to give you full credit. Draw a diagram showing all the values before you begin the problem. There's my diagram. I'm showing the industrial load out here, consuming an average power of 100 kilowatts, which I get from up above here. Power factor is 0.8 lagging, which I get from the statement up above. I know that the line current is what goes to the load. It's 200 amps RMS, which is what I get up above here. And I'm going to solve for V of the load RMS. Everything I need is right there. I just look for equations. If this confuses you, just look for a couple equations. It's finding 2 out of 3 most of the time. Or 3 out of 4 most of the time. I just go down here and I say, well, I know the power in the load is equal to voltage in the load RMS times I in the load RMS times the power factor. I wrote it as cosine of phi, but that's the equation. So I go straight to power in the load is equal to voltage in the load RMS times current in the load RMS times the power factor. I isolate voltage in the load RMS because that's what I'm trying to find up here. I plug in all the values and I get my answer of 625 volts RMS. I took that all from that block diagram. The statement problem to the block diagram, look for equations and you solve it. Let's do another one. Industrial example number 2. An industrial plant with an inductive load consumes 10 kilowatts of power from a 220 volt RMS line. Most of the time the industrial plants, the machine shops, the manufacturing facilities, they're all going to be in inductive loads. I can't think of a situation where you have capacitive loads out there at a facility. Very unlikely. Mostly motors that are out there. So an industrial plant with an inductive load consumes 10 kilowatts of power from a 220 volt RMS line. If the load power factor is 0.8 lagging, what is the angle by which the load voltage leads the load current? Draw a diagram showing all the known values before you begin the problem. There's my diagram. The plant, back here we have the generating facility. And this right here is some type of industrial plant, assuming the power in the load that it's consuming out here is 10 kilowatts. I get that from up here. The power factor is 0.8 lagging. I get that from up here. I know that the line voltage that they're using is 220 volts. I know it's RMS. I get that from up here. I have everything I need here. Find the angle. You basically want to find the difference between the voltage and the current, but that's the impedance angle. They don't tell you that up here, but that's what it is. So I get straight to here. This 10 kilowatts, this 220 volts, it does nothing to this problem except maybe make you nervous. Look at what they want. Everything's in terms of the power factor. I know what the power factor is equal to. I know that the power factor, let's write it down. The power factor is equal to the cosine of the angle between the voltage and the current. I know that. So how do you solve that for that angle? You solve that for that angle by taking the inverse cosine of the power factor. So the inverse cosine of the power factor is equal to 36.87 degrees. So the angle has to be 36.87 degrees. That's your answer. And the voltage leads the current by 36.87. They gave you that up here. All that's telling you is it's an inductive load. That's all. A little redundancy in their comment. But that's 36.87 is the answer. Let's do example number 3. Another problem in the book. West Penn Power must generate 100 kilowatts to supply an industrial customer with 94 kilowatts through a transmission line that has a 0.09 ohm resistance, which is an application there. That's typical. Very, very low resistance in the transmission lines, but there's still some resistance there. If the load power factor is 0.83 lagging, find the RMS load voltage, VRMS. Don't forget to draw that diagram. So I drew a diagram here. I have the power supplied, P sub S here. I show my line resistance. It's distributed resistance. I just put a resistor there. R sub L is 0.09 ohms. Here's my load. My load out here, they say, is power in the load. Average is equal to 100 kilowatts at a 0.83 lagging. I'm sorry. Let's have to take a look at this. West Penn Power must generate. So the power they must generate out here, the power at the source, they give you the power at the source. So this power at the source is equal to, it's equal to 100 kilowatts. And they have to supply 94 kilowatts through the transmission line to the customer. So what they have to do out here is they have to supply 94 kilowatts. There's what we have. The power supplied back here is 100 kilowatts. I have some line resistance right here. And the power that the customer needs is 94 kilowatts at a power factor of 0.83 lagging. Find the RMS load voltage. What's this voltage have to be? What's that voltage have to be right there in the line? If that load resistance if that line resistance is 0.09 ohms. I have everything I need right there in that diagram. You take a look and you know that the power supplied back here, the total power supplied has to be the power in the line, the power in the load out here, the power that the customer needs, plus the power that's lost in the line, because the generating company back here, West Penn Power, has to generate all that power, the power for the loss and the power that goes to the customer finally needs. So using that equation and knowing what the current is, or knowing what the line voltage is, I can solve for the current. I know the power supplied, I know the power in the line, I know the line resistance. Isolate the variable I get the current. Once I get the current, I can find the load voltage, the line voltage. So the voltage in the load, the voltage at the line, same thing. It's the voltage out here. It's that voltage right there. Turns out to be 438.63 volts RMS. And there's that problem. A simple conservation of power, my I squared R equation, that's the loss in the line, isolating I, finding my line voltage, knowing the power, the current, and the power factor. And then finally, industrial problem number 4. West Penn Power supplies 80 kilowatts to an industrial customer. The load draws 220 amps RMS from a line, from the transmission line. If the load voltage is 440 volts RMS and the load power factor is 0.8 lagging, find the losses in the transmission line. Draw a diagram showing all the values before you begin the problem. So I showed the problem, I wrote down the values based on this problem here. I'm searching for equations. The first thing that comes to mind is I know my power in the load, okay, has to be equal to this. It looks like they give me my 440. Looks like they give me my 220. Looks like they give me my power factor. So it seems to me I can find that power in the load. Okay? So let me say I get 77.44 kilowatts. Power in the load here. Let me see if I drew this right. Make sure I drew that right. West Penn Power supplies 80 kilowatts to an industrial customer. Okay. The load draws this from the transmission line. If the load voltage is this, find the losses in the line. Okay. That's wrong right there. That 80 kilowatts shouldn't be out there. That's what did this in the last problem. That's what West Penn Power supplies. West Penn Power supplies 80 kilowatts to an industrial customer. Make sure you draw that right. This should have been a lot bigger here when I drew it, and then you have to calculate out here based on the line voltage and the load voltage what the power in the load is going to be. And that's what this 77.44 kilowatts is. 77.44 kilowatts. That's the power that the customer uses. How do I know that? Because there's the 440 volts that's the line voltage, and there's the current, and there's the power factor out here. Now, I would have known all that if I would have drew this and I would have put the values that I have here on this side. I would have surely put the power and the load equals with a question mark. I would have said the current and the load current, the load voltage, and the power factor lagging is all load related here. And then I would have went right to this equation to start out. I would have found power in the load at 77.44 kilowatts. I would have realized that the power supplied by West Penn Power has to equal the power that the customer uses plus the power that's lost in the line. And when I subtract those two, that would give me the power that is lost in that distributed line resistance up here, which turns out to be 2.56 kilowatts, which is what they want for an answer. And then I left this last one here for you to go ahead and take a look at. I want you to try this one on your own. So just go ahead and read that problem, get a piece of paper, read the problem, get a piece of paper, see if you can't draw that figure based on this information the way I'd want you to draw it. Show the diagram, and then work it out and see if you get that answer. See if you get my solution right there. The power in the line that's lost is 1.6 kilowatts. And that concludes this lecture.